So we are going to study robotics. We are going to talk about articulated robots or robot arms. So robot arms. They are also called as articulated robots. Now please understand, a physical robot may look different than its geometric representation or its kinematic representation. As an example, your physical robot may look something like this. But for the analysis purposes, we want to decompose this robot into the links and the joint. So in this robot, please note that you have the first joint. This is the shoulder joint. Then you have the elbow joint. And then you have finally here, you have the end effector. So you have multiple joints. In robotics, there are two types of joints. One is a rotary joint or the hinge joint. So that is called as revolute joint. So revolute joint. So the revolute joint is nothing but a hinge. And this revolute joint is going to look something like this. So you have a link, and at the end of the link, that you have a hinge. So this is the revolute joint. This revolute joint is denoted by R. The other type of joint is prismatic joint. Prismatic joint, it is like a piston cylinder assembly. So piston cylinder. So if you think about it, it looks something like this. So this kind of reciprocates forward and backward. If you look at the revolute joint rotates. So you have the angular displacement and then you have the linear displacement. So you have angular displacement, and you have the linear displacement. Now you can have very complex robotic system, but at the end of the day, that complex robotic system can be decomposed at combination of revolute joints, prismatic joints, and links. For an example, the robot that you have in front of you, which would be similar robot that you'll be using for the lab, you have your first revolute joint, you have your second revolute joint, and then you have your third revolute joint. Now, this robot, if you look at its configuration, may look different. But when you are trying to analyze the robot, you want to come up with a simplified representation of the robot. And that is called as the kinematic diagram. So kinematic diagram, is the simplified representation of robot when joint angles are 0 and robot is fully extended. So we will talk about what is kinematic diagram in just a minute. If you look at the revolute joint is represented something like this. And please note, we are going to draw the robots in 3 dimensions. So we are going to show the revolute joint something like this. So this is the representation of the revolute joint. If you look at the prismatic joint would be shown something like this. And what this means is prismatic joint is translating in the direction that is shown. So revolute joint gives you the rotation, prismatic joint gives you the translation. When you study robotics, you are going to deal with different coordinate systems and different frames. Now, why is this important? Now, please try to understand is if you look at the robot, your robot is moving in 3 dimensions. So in 3 dimensions, you have different references. You can have a ground reference, you can have a moving reference, you can have a reference that is attached to the end effector. So all these are different coordinate frames. So the most important part is to understand how these coordinate frames are related to each other. How do we transform from one coordinate frame to other coordinate frame? Now in robotics, we use right-hand coordinate system. What is this right-hand coordinate system? Right-hand coordinate system, so right-hand coordinate system. So what is this right-hand coordinate system? In the right-hand coordinate system, you have a triad. Triad means 3 mutually perpendicular axes. This is your x-axis, this is your y-axis, and this is your z-axis. So now how do you identify which axis is x, which axis is y, and which axis is z? So for that, you will use your right hand. And then you have the thumb, you have the first finger, and you have the middle finger. Now think about it. When you are drawing on a graph paper, the horizontal axis is going to be the x-axis, vertical axis is going to be your y-axis. So your thumb is your x-axis, the first finger is your y-axis, and your z-axis is coming out of the board. Now, if you had something like this, if you have x-axis, you have y-axis, then your z-axis is gonna go down. So you are gonna have coordinate system that is oriented in this 3-dimensional space. But no matter how the coordinate system is oriented, you would be following right-hand coordinate system, right-hand thumb rule. Now let's talk about the rotations. You are going to have 3-dimensional rotations. So to identify if the rotation is positive or negative, you will curl your fingers, right hand. You will curl your fingers in the direction of rotation. If your thumb is pointing toward the positive axis, that rotation is positive. What do I mean by that? So check this out. So look at this rotation. Curl your finger in the direction of rotation. Your thumb is pointing towards positive x-axis. So this rotation is positive. So look at this. Curl your finger in the direction of rotation. Can you see your thumb, right hand thumb, is aligned with positive y-axis? So it is positive. If you look at z-axis, curl your finger in the direction of rotation. and your thumb is aligned with positive z axis. So this rotation is positive. If you curl your right hand fingers and if your thumb is pointed towards negative x, negative y, or negative z, that rotation is negative. Everyone understood this? So for all our robotic systems, we are going to use the right hand coordinate system. Everyone understood this? Okay. Now, the one important thing that we want to understand is where are these frames located? So let me start with a very simple robotic problem. So as I discussed earlier, we are going to study initially two important things. We are going to study forward kinematics, and then we are going to study inverse kinematics. What is forward kinematics? Forward kinematics is given the joint variables, given the joint values, what is the position of the end effector? Let me write this down. Forward kinematics. Forward kinematics. So forward kinematics is given joint angles or joint values, find position of end effector. So I'm going to give you a simple problem. Imagine that you have 1 degree of freedom robot. So imagine that you have a robot and this robot has this one link and this robot has one hinge. So this is the rotary joint or revolute joint and you have the hinge. Now this hinge is fixed to the ground. So what I'm going to do is I'm going to assign a coordinate system that is fixed to the ground. So I'm going to draw a coordinate system. This is my coordinate system. This is my x coordinate. This is my y coordinate. And this coordinate system is fixed. Why is this fixed? Because I want to find out the location of the end effector in terms of the fixed or the inertial coordinate system. This is also called as the fixed or inertial coordinate system. And you have this link. The length of this link is L. The length of this link is L. Now, please understand, this is the right-hand coordinate system. You are going to have X, you are going to have Y, and Z is coming towards board. Now, if I show you this rotation, do you agree with me? Curl your fingers in the direction of rotation. This rotation is in the same direction as positive Z. So this rotation, which is counterclockwise, is positive. This angle is theta. This guy is the end effector. This is the end effector. So the forward kinematics is, given the value of theta, what is the position of the end effector? So what is Px and what is Py? So the question is, end effector position is given as Px and Py. So given theta, say theta is given, you have to find out Px and Py. So you have to find out what is the value of Px and Py. That is the forward kinematics problem. Now to solve the forward kinematics problem, this is a single link problem. So it's very easy. So what I can do is, I can draw vertical line and say that this distance is L cosine theta and this distance is L sine theta. So Px is equal to L cosine theta and Py is L sine theta. Now please note that this L is the robot parameter. So this L is given to us. L is not changing. The only thing that is going to change is the value of theta. Say if you have a motor, that motor will rotate this link and accordingly value of Px and value of Py would be changing. Everyone understood this? Now this is the forward kinematics. What is inverse kinematics? Inverse kinematics is given values of end effector position. EE stands for end effector position, which is Px and Py. Find values of theta, so of joint angles. Now, which means I will give you the value of Px and value of Py, and you would find out the value of theta. So Px and Py, Px will be given to you, Py will be given to you, and then you have to find out what is the value of theta. So that is called as the inverse kinematics. Forward kinematics means you substitute the value of theta, get the value of Px and Py. Inverse kinematics is Px and Py is given to you, and using the robot geometry, you find out the values of theta. Now, please try to understand. Forward kinematics problem can be solved, which means you substitute the value of theta and get the value of Px and Py. But inverse kinematics problem may have a solution, may have multiple solutions, or there may be no solution. So for inverse kinematics, you can have one solution, you can have multiple solutions, and you can have no solutions. So let me give you an example. So in the problem that is given here, how would you find, if I give you value of Px, if I give you value of Py, how would you find theta? You'll find the ratio of Px by Py, and then you will do a tan inverse of that, right? So for an example, so if you want to find theta, theta is equal to, you will say Py by Px. So Py by Px, to find theta, let me see, Py by Px is nothing but L sine theta divided by L cosine theta. So you are gonna get tan theta. So if you want to find out theta, theta can be found out as tan inverse of Py by Px. Now please understand, for certain values of tan is undefined. So one thing I want to tell you is, imagine if I give you Px and Py over here. If I give you Px and Py, which is outside the robot work envelope, physically robot cannot reach that Px and Py. So clearly there is no solution. Sometimes what happens is, because of the robot geometry, certain positions inside the workspace may not be reached. For example, you have articulated robot, and then you are looking at some position which is folded inside. Even though you can visualize that position, but physically that position cannot be achieved. So that's kind of a dead zone. Now, in certain cases, I want to give you an example. Imagine if you have a two-link robot. So if you have a two-link robot, and this is the end effector position. This is the end effector position. This end effector position can be reached by elbow on top or elbow on bottom. So your robot, this two-link robot, it has two different configurations that will attend the same end effector position. So which means you can have like this. So your angles are going to be different. So this is one solution and this is other solution. So you can have, for forward kinematics, substitute the value of theta, get the value of Px, Py, and Pz. That's very straightforward. For inverse kinematics, there may be a solution, there may be multiple solutions, or there could be no solution. So how do we solve this inverse kinematics problem? So when I was a student, we had to do this mathematical jugglery and then solve this inverse kinematic solution. But nowadays, what we do is we use computer simulation software like MATLAB, and then MATLAB gives us the inverse kinematic solution. So in today's class, I will be working out the calculations by hand. I would do the matrix multiplications by hand. The next class onwards, we will use MATLAB to solve. In today's class, I will do the matrix multiplications by hand. But next time onwards, please install MATLAB on your computers. That is available at ASU My Apps. And you have to install the robotic toolbox. And then we will use MATLAB to solve robotic problem. Now, one thing I want to talk about is, we talked about this simple robot where the frame is fixed or the frame is inertial. Inertial means lazy. Inertial means non-moving. But it is quite possible to have one more frame which is attached on to this link. So now what I want you to do is, I want you to pay close attention. In the robot, I have drawn two coordinate systems. One coordinate system is fixed to the ground, and the other coordinate system is fixed to the link. Which means as that link is rotating, that coordinate system is rotating. Now imagine if I were to add one more link, that link would have its own coordinate system. If I add one more link, that link would have its own coordinate system. So I need to keep track of the fixed coordinate system and the moving coordinate system and the relationship between these two coordinate systems. This is an extremely important point. So whenever you are studying robotics, you are trying to understand how these coordinate frames are moving with respect to each other. When you study robotics 2, which is aerial robotics, again you are going to have coordinate systems. So you want to study how these coordinate systems rotate or translate or move with respect to each other. So we are going to spend some time in understanding the coordinate system and their rotations. So as promised, before I go to the next part, which is extremely important, let me quickly review what we studied. At the end of today's class, we are going to have a quiz based on the material that we have discussed. That quiz will be closed book, closed notes, closed tablets, closed laptop, no phones allowed. So if you are taking notes on computer or in a tablet during the break, I strongly recommend that you rewrite those notes or at least summarize those notes on a piece of paper. We talked about different types of joints in the robot. You have prismatic joint, they indicate rotational motion, and there is rotary joint or the revolute joint that indicates the rotary motion. Your robot may have complex joints. So for example, robot would have a shoulder joint, but the shoulder joint is represented as two revolute joints which are perpendicular to each other. We also talked about something called as the kinematic diagram. Kinematic diagram is the simplified representation of robot so that we can write mathematical expressions for the forward and inverse kinematics. So please try to understand, if I give you a physical robot may look different, but for calculations, to derive the expressions of forward kinematics and inverse kinematics, this robot can be decomposed into its joints and links. So here is a revolute joint, revolute joint, revolute joint. Very important. The first revolute joint is perpendicular to the second revolute joint. Third revolute joint is parallel to the second revolute joint because the robot is a three-dimensional system. So you have joints which are in different orientation. And we will study in this class how to solve this three-dimensional system using the mathematical tools that we already know. We will always use right-hand coordinate system, which means curl your fingers, your thumb is X, first finger is Y, second finger is C. Always use right-hand coordinate system because you are going to have coordinate systems in three dimensions. And you will notice that when you have three-dimensional coordinate system, identifying X, Y, and Z is extremely important. Otherwise, your calculations will go wrong. The other sign convention is curl your fingers in the direction of rotation. If your thumb is pointing in the positive x-axis or positive y-axis or positive z-axis, that rotation is positive. So we will always deal with right-hand coordinate system and positive rotation. That's the important part is solving forward and inverse kinematics. What is forward kinematics? Forward kinematics is given the geometry of the robot, given the joint angles. Find out the position of the end effector. So I want to find out if I give the joint value for the first joint, say 30 degrees. If I give joint value for the second joint, 40 degrees. If I give joint value for the third joint, 50 degrees. I want to find out in this configuration where this end effector is going to be. That is the forward kinematics problem. Everyone understood? Forward kinematics problem has unique solution, which means I substitute the value, and for the given values of theta, I know there will be a px, py, and pc. So I give an input and output is guaranteed. The inverse kinematics problem is slightly different, wherein you give the values of the end effector positions and you want to find out the joint angle. What is the end effector? End effector is the end point or the end coordinate system of the robot. So here, this is the end effector, because if I want to attach a pen, or if I want to attach a welding torch, or if I want to attach a paintbrush, whatever I want to do, I want to attach to the last final coordinate system. That coordinate system is called as the end effector. Inverse kinematics may have a solution, may have multiple solutions, or may not have any solution. Now, solving inverse kinematics problem can be challenging, but we are going to use MATLAB to solve inverse kinematics problem. Okay, next part, which is extremely important, and I want everyone to pay attention, is we are going to derive rotation matrices. So now here is a problem. So we have two coordinate systems. So we have two coordinate systems. This coordinate system, I'm going to call x naught and y naught. And for x naught and y naught coordinate system, the triad z naught is coming out of the board. The triad z naught is coming out of the board. And I'm going to find the rotated coordinate system, which is x1 and y1. So what you have is you have this coordinate system. This is x1 and y1. Now, please note what I'm trying to do. I'm going to find out the relationship between these two coordinate systems. Since x naught is perpendicular to y naught and x1 is perpendicular to y1, if this angle is theta, you agree with me that this angle is also theta, because x and y, x naught and y naught, x1 and y1 are perpendicular to each other. Do you agree with me? Now what I want to do is, and it's extremely important, I want to find out projection of x1 and y1 on x naught and y naught. And I'm going to go very slow, but what I'm doing here is extremely important. The rotation matrix that we are going to derive here will be used throughout the course. This is the only rotation matrix that we are going to use. So please try to understand. I'm going to find projection of x1 and y1 on x naught and y naught. So how do I do this? So to do this, I'm going to extend this axis and I'm going to draw perpendiculars. So I'm going to draw perpendiculars. So first, you see that this distance is going to be x1 cosine theta. You agree with me? This distance is going to be x1 cosine theta. You agree with me that this distance is going to be y1 sine theta, because this guy is y1 sine theta. So this guy is going to be y1 sine theta. Do you agree with me? One thing that I want you to note, that I'm going to show you the vector direction. So this vector is going to be in this direction. This vector is going to be in this direction. This vector is going to be in this direction. This vector is going to be in this direction. Why do I have directions like these? Because please try to understand. This vector is the resultant of this vector plus this vector. In other words, to get to this point, you need to go forward in x0 direction, turn and go upwards in y0 direction. To get to this point, you need to go in negative x0 direction and then plus y0 direction. So everyone understood the arrows? What that means is very important, that this x1 cosine theta component is in positive x0 direction and y1 sine theta component is in negative x0 direction. Can you see that this component is aligned with positive x0 axis? This component is in the negative direction. So if I want to write down the projection equation, I will write this down like x0 is equal to x1 cosine theta minus y1 sine theta. Do you agree with me? Why is it? Once again, because if you look at the projection, x1 cosine theta is in the same direction as x0, so it's positive. y1 sine theta is in the opposite direction of x0, so this is minus. Now let's look at the projection in the y direction. So this projection is x1 sine theta and this projection is y1 cosine theta. You agree with me? Look at this projection, y1 cosine theta. So this projection is y1 cosine theta. This projection is x1 sine theta. But please note, both these components are in the positive y0 direction. So can you see that this y1 cosine theta is going in the same direction as y0? x1 sine theta is going in the same direction of y0. So if I were to draw y0, is going to be x1 sine theta plus y1 cosine theta. Now one thing, last but not least, remember your z0 is coming out of the board. Your z0 is coming out of the board. Your z1 is also coming out of the board. But do you agree with me that z0 and z1, both of them are aligned? Which means I can write this down as z0 is equal to z1. Do you agree? So now what I have is I have these three algebraic equations and I want to write them in a matrix form. I have these three algebraic relations and I want to write them in a matrix form. So what I would do is I will go something like this. I'll say x naught, y naught, z naught. And I'm going to have this matrix. I'm going to have x1, y1, z1. So what I need to do is I need to fill in the blanks. So do you agree with me? So this is a 3 by 3 matrix. So I need to fill 9 blanks. So what would be here? You agree with me? There will be cosine theta. What would be here? Minus sine theta. You agree with me? Here it will be 0. Now check this out. We want to perform the matrix multiplication. First row, first column, cosine theta times x1 minus sine theta times y1 plus 0 times z1. I get the first equation. The next one is you have y naught, which is sine theta cosine theta 0. So y naught is sine theta times x1 cosine theta times y1 0 times z1. You agree with me? And the last will be 0, 0, 1. This is the most important matrix that you will use in robotics 1. This matrix is simply cosine theta minus sine theta, cosine theta, and at the diagonal, it would be 1. Please note, when you have 1 in the diagonal, the other elements are going to be 0. So here there will be 0, here there will be 0, here there will be 0, and 0 over there. Now, there is one more thing that I want you to remember. So, I want you to read the problem statement. I want to find out projection of, projection on. I want to find projection of x1, y1, z1 on x0, y0, z0. Now, this I want you to understand why is this important. Because your initial frame is x0, y0, and z0. Your next frame is x1, y1, z1. So you are finding out projection of the new frame onto old frame. It will always be like this. New, from new to old. So here is a simple trick that I want you to remember. And remember this matrix. So you have x1, y1, z1. This is projection of. And why this is also the new frame. This is the new frame. New. And projection on x0, y0, z0. This is projection on. And this is old. Now I want everyone to pay attention. This type of structure you will see again and again, when you solve forward kinematics problem. Because please try to understand, as you keep on adding links, you are gonna have maybe frame x2, y2, z2. So you wanna find out projection of x2, y2, z2 on x1, y1, z1. Projection of new onto old, new to old. So now check this out. So I want you to look at the figure that we have here. So projection of x1 on x0. Do you agree with me? It is cosine theta. Projection of x1 onto x0 is cosine theta. Projection of y1 onto x0. Projection of y1 onto x0 is sine theta. But that's a minus sine theta. Projection of z1 onto x0 is 0. Why? Because they are mutually perpendicular. Now projection of x1 onto y0 is sine theta. Projection of y1 onto y0 is cosine theta. Projection of z1 onto y0 is 0. Projection of x1 onto z0 is 0. Projection of y1 onto z0 is 0. And projection of z1 onto z0 is 1. Do you agree with me? So you got the same rotation matrix. Now this rotation matrix is the rotation about z. Because notice that x0, y0, z0 and x1, y1, z1, they are rotated like this. Similar rotations can be obtained about x, they can be obtained about y. The procedure is exactly the same. But we are not going to use the rotation matrices. But maybe I'll ask you that question in the quiz. Like derive the rotation matrices about x, derive the rotation matrices about y. And you will follow the exact same process the way I have done. Either you can formulate the algebraic equation and convert them into matrix form, or you can use this technique, projection of new frame onto the projection of old frame. And you will get the same rotation matrices. You will not forget these rotation matrices because all forward kinematics problem will use the same rotation matrix. Cosine theta, minus sine theta, sine theta, cosine theta, and you will have one in the diagonal. Everyone understood this? So I'm going to stop here. Let me pause the recording. So now what we are going to do is we are going to solve a forward kinematics problem. So to solve forward kinematics problem, I'm going to show you a three-dimensional robot. So if this robot is something like this. Fine, look at that figure. So this robot has two revolute joints. This is the first revolute joint and this is the second revolute joint. So this is robot first revolute joint. This is robot's second revolute joint. This is the end, end effector of the robot. This is the end effector of the robot. Now you can have a motor here that will rotate this first link. You can also have a motor here that will rotate the second link. So there are two links and two revolute joints. Do you agree with me? So now what I'm going to do is I'm going to give you some dimensions. So this dimension is A1. This dimension is A2. This dimension is A3. And this dimension is A4. Now, please try to understand your physical robot would have some thicknesses. Physical robot may have different configurations. But now what we want to do is, from this physical configuration of 2 degree of freedom robot, we have to construct the kinematic diagram. So what I need to do is, as you can see, there is link number 1, there is link number 2, there is motor number 1, motor number 2, so 2 revolute joints and 2 links. So I'm going to construct the kinematic diagram. The kinematic diagram for this robot is going to look like this. This is the first revolute joint. Then you have the second revolute joint. And then you have this link. And this is where you have the end effector. So what you have is you have the first revolute joint, you have the second revolute joint, and you have the end effector. Now please note that the first revolute joint is fixed to the ground. So this first revolute joint is fixed to the ground. This link distance is A1. This link distance is A2. This link is A3. And this link is A4. So you have A1, you have A2, you have A3, and you have A4. Now, most important thing is we have to identify the coordinate systems for different links. So first and foremost, let me give you a rule, set of rules. The first rule is z-axis goes through joint. So which means I'm going to first specify the z-axis. So this axis is going to be z0. Second axis is going to be z1. And then at the end, we have an end effector. Just for simplicity, I'm gonna assume that Z0, Z1, and Z2, they are like this. So you have Z0, you have Z1, and you have Z2. Now let me give you the second rule. Second rule is very important. Now I need to find out where the x-axis is gonna be. So the rule is xn is perpendicular to Zn minus 1 and intersects Zn minus 1. What do I mean by that? So for an example, if I have an x-axis, x1, it needs to be perpendicular to Z0 and intersect Z0. And I'll explain to you what I mean. So I have this Z0. So I have to identify X0. But do you agree with me? In this diagram, there is no Z minus 1. The whole diagram starts with Z0 or Z0. There is no Z axis before Z0. So I'm going to assume my X0 to be in this direction. And it doesn't have to be in this direction, but you can assume it to be any direction you want. But I'm just assuming this X0 to be in this direction. You can also assume X0 to be in this direction. You can also assume X0 to be in that direction. That does not matter. But this is how I'm assuming my X0. Now comes the important question. I want to find out where should I draw X1? X1, you agree with me? X1 has to be perpendicular to Z1 because it's part of the triad. But that X1 should intersect Z0. And this is a very important problem. So please try to understand. So what I'm going to do is, I'm going to show you potential locations of X1. So as shown over here, you can have X1 in this direction. You agree with me? You can also have X1 in this direction. You agree with me? You can also have X1 in this direction, or you can have X1 in that direction. So you have 4 possible directions for X1. And now the question is, where would you draw X1? Now please try to understand. If I draw X1 here, or if I draw X1 here, do you agree with me that this X1 will be perpendicular to Z0, but will not intersect Z0? Why? Because there is this offset A2 between X1 and Z0. Do you agree with me? There is an offset. So if I draw this here, or if I draw this here, the rule will not be satisfied. So the only option is I need to draw X1 here or here. So the only option is I need to draw X1 in these 2 directions. So now the question is, where would you draw X1? If I draw X1 in this direction, do you agree with me? X1 is perpendicular to Z1, X1 is perpendicular to Z0, and X1 is intersecting Z0. Do you agree with me? I can also draw X1 in this direction. I can draw X1 in this direction. It will also satisfy the same thing. The only problem is this X1 will be in the opposite direction of X0. And that may lead to some difficulties later. So for the time being, just for simplification, I'm going to assume X1 in this direction, which is the same direction as X0. So what I'm going to do is, I'm going to assume X1 in this direction. Do you agree with me? Now, same argument goes for this. So I have two potential positions for x1. Now, if I use, now I need to specify x2. If I use this or this direction for x2, x2 will be parallel to z1. x2 will be parallel to z1. So the only viable option is x2 here or here. Do you agree with me? But for simplicity, you want to make sure that all these coordinate frames are similar to each other. I'm going to assume x2 in this direction. x2 and x1. Once again, let me explain. x0 can be anywhere. Why? Because there is no other z-axis before z0. So x0 could be anywhere. x1 needs to be in that orientation because x1 needs to be perpendicular to z0, perpendicular to z1, and it needs to intersect z0. In other configuration, x1 does not intersect. In other configuration, x1 does not intersect. Now, if you look at x2, x2 needs to be perpendicular to z1 and z2 and should intersect z1. So that position is the right position for x2. Now, I have constructed z0, I have constructed x0. Now I need to complete the triad. Remember triad? So this is my x0. This is my z0. So my y0 needs to go inside the board. You agree with me? This is my x. This is my y. This is my z. So I'm going to align z and x. And can you see y is going in? So this is going to be my y0. Do you agree with me? Similarly, x, z, can you see y is going in? This is y1. Now, x2 and z2, can you see y2 is going in? Setting up coordinate system is an extremely important exercise. So whenever you have a forward kinematics problem, you will be given a robot. You have to draw the kinematic diagram. Once you draw the kinematic diagram, you have to identify the coordinate frames. So you will start with the 0th coordinate frame. The 0th coordinate frame would be fixed or inertial coordinate frame. So forward kinematics problem is nothing but identifying the position of end effector in x direction, in y direction, and in z direction with respect to the initial or the first coordinate frame. So you have to find out the position of the end effector with respect to the inertial or the first coordinate frame. To find coordinate frame, you have to follow the rule. Rule number 1, the z-axis must pass through the joint. X-axis should intersect z n minus 1 axis. And at the end, you have to complete the triad. Everyone understood about the coordinate system? Now let's understand the rotations. So this joint is rotating. This joint is rotating. I'm going to assign positive rotations for these two. So there will be theta 1 and then there will be theta 2. Do you agree with me? There is theta 1 and theta 2. Let me use a different color. So this is theta 1 and this is theta 2. This is theta 1 and this is theta 2. Curl your fingers in the direction of theta and you will notice theta 1 is positive, theta 2 is also positive. Have you noticed one important thing? That the rotation is about z-axis, which means the rotation matrix that we are going to use is the same rotation matrix that we derived a moment ago. Cosine theta minus sine theta, sine theta, cosine theta. Everyone understood this? Now we'll start deriving the rotation matrices. So first and foremost, I want to derive the rotation matrix 0, R, 1. So 0 stands for the 0th frame. R stands for the rotation matrix. And 1 stands for the first frame. And this is always old frame R and new frame. Now, since the rotation is about z-axis, rotation is theta 1. I can write down the rotation matrix cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Do you agree with me? This is the same rotation matrix that we derived a moment ago. Now, one thing I want you to keep in mind. Every rotation matrix needs to be multiplied by the projection matrix. What do I mean by projection matrix? So please understand your x1, y1, z1 may or may not be aligned with x0, y0, and z0. So you need to understand the projection. And we also did that. And remember, the projection matrix is projection of, projection on, projection of new frame onto projection of old frame. So new frame is x1, y1, z1. This is the new frame. And the old frame is x0, y0, z0. Now I want you to look at the diagram. I want you to look at the diagram. We are doing the same exercise that we did before. Can you see x1 is aligned with x0? Can you see the direction of x1 is in the same direction of x0? So here there would be 1. You agree with me? Here there would be 1. x1 has no relationship with y0, no relationship with z0. So here there will be 0, here there will be 0. y1 has no relationship with x0. So 0 here, but please note y1 is aligned with y0. So you are going to have 1 here. y1 has no relationship with z0, so 0 here. z1, no relationship with x0, y0, and 1 at the diagonal. So you are going to have an identity matrix. And this is extremely important. So please try to understand this matrix is going to look like 0, 1, 1, 0, 1, 0, 0, 1. This is identity matrix. Now remember, when we were identifying the coordinate frame, we had option. We could have assumed x1 going towards right, or we could have assumed x1 going towards left. We could have assumed x1 going towards right, or we could have assumed x1 going towards left. If we would have assumed x1 going towards left, do you agree with me that x1 would be in opposite direction of x0, and then there would be a minus sign here. But since what we did is we drew the coordinate system x1, y1, z1, which is perfectly aligned with x0, y0, z0. We solved ourselves a little bit of trouble of changing the sign. The problem is not wrong if you change the x1 going towards left rather than going towards right. That would still give you the answer. But then your projection matrix is going to have negative signs popping up. And we will solve those problems. But right now, the argument here is the frame x1, y1, z1 is aligned with the frame x0, y0, z0. That's why the projection matrix is an identity. Projection matrix will always be projection of new frame on old frame, of new frame on old frame. Same thing that we did earlier. Everyone understood this? Do you agree with me that if you multiply any matrix with an identity matrix, you get the same matrix? Now, next thing is a little bit you want to be careful. Now, rotation matrix encodes the rotational information, which means how are these two frames related in rotation. But please understand, these two frames are also translated. They are not on top of each other. These two frames are apart from each other. So there is the translation between the frame, and we need to capture this translational information. We need to capture this translation information. So what we are going to do is we are going to write homogeneous transformation. Homogeneous transformation is a 4x4 transformation that captures the rotational information, rotation transformation, and translational transformation. So this homogeneous transformation is shown as 0 H1. This homogeneous transformation is a 4x4 matrix. In this 4x4 matrix, on the left hand side, you have the rotation matrix. And this rotation matrix is going to be the multiplication of the rotation matrix multiplied by the projection matrix. And I'm going to write this over here. This after multiplying these two matrices, I'm going to get cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. And this homogeneous transformation is a 4x4 matrix. So the last row of this homogeneous transformation, is going to be 0, 0, 0, and there will be 1. Now comes the most important part. This. So first row, fourth column gives you the translation about X. First row, fourth column is the translation about X. Second row, fourth column is translation about Y. Third row, fourth column is translation about Z. Now what I want to do is, I want you to kind of look at these two frames. I want you to look at these two frames. Okay, I want you to look at these two frames and observe there is a translation by A1 in the Z direction, and there is a translation by A2 in the X direction. There is no translation in the Y direction. Do you agree with me? The way I have drawn the figure, there is translation in Z direction, there is translation in the Y direction, X direction, but there is no translation in Y direction. Now, it is extremely important. Wherever you are writing the translation would be in the old reference frame, which means this would be the X translation in X0 reference frame. So this guy is going to be X translation in X0 frame. This is Y translation in Y0 frame. And this Z translation in Z0 frame. So please try to understand. You are dealing with two frames. The old frame is X0, Y0, Z0. The new frame is X1, Y1, Z1. You want to find out how far apart these two frames are. But you cannot just arbitrarily write the frame distances. That dimension is a vector, which means it needs to be in certain coordinate frame. So the distance between the new coordinate frame and the old coordinate frame must be expressed in the old coordinate frame. What do I mean by that? So if I want to go from the 0th frame, so this is 0th frame, and I want to go to the first frame, I need to travel A1 unit in the Z0 direction. A1 unit in the Z0 direction. And the way I have shown here is A2 units in X0 direction. You agree with me? If I want to go from the 0th frame to the first frame, 0th frame is the intersection of X0, Y0, Z0. First frame is the intersection of X1, Y1, Z1. If I want to go from the 0th frame to the first frame, I need to travel A1 unit in Z0 direction, and the way I have shown here, A2 units in X0 direction. Everyone agrees with this? Now please understand, these relationships should be valid for all the values of theta. Which means even though the value of theta is 0, value of theta is 30, value of theta is 40, these translations should remain valid. Now you agree with me that here I'm assuming theta is equal to 0. That's why I'm traveling A2 unit in X2 direction. But if theta is say 20 degrees, 30 degrees, 40 degrees, do you agree with me? The distance in X2 direction will be A2 cosine theta 1. Now for that, if you don't agree with me, here is what I want you to do. Let me give you an example. So this is basically the robot. You are looking from top. This distance is A2 when theta is 0. But now you are providing a positive rotation. So when theta is rotated by a positive direction, can you see this X0 distance is going to be A2 cosine of theta? Look from top. And you see A2 cosine theta is the distance in the X0 direction. Have you understood why A2 cosine theta? If theta is equal to 0, A2 cosine theta becomes A2. And that is the case shown over here. But you need to make sure that the distances between these two coordinate frames should be valid for all possible values of theta. The distances should be valid for all possible values of theta. So can I write A2 cosine theta 1 here? What would be the distance in the y naught direction? It would be A2 sine theta 1. And I want you to kind of notice, if you look from top, so if you look from top, then you will notice this has y naught, this as x naught. Now when theta is 0, you would see A2 like this. When theta is non-zero, if this is your A2, then you are going to have cosine A2 cosine theta 1, and you are going to have A2 sine theta 1. Do you agree with me? And what about Z naught? What about Z naught? No matter what is the value of theta, the Z distance between the 0th frame and the first frame is not going to change. So that will be A1. Do you agree with me? So I will explain this once again because this is extremely important. So I want you to understand this. So what happens is we have this rotation matrix. Rotation matrix will start with the rotation about Z, which needs to be multiplied by the projection matrix. And the projection matrix will be projection of new frame onto old frame. And then once you multiply the rotation matrix and the projection matrix, you are going to get this final rotation matrix. That would be the first 3x3 matrix in the homogeneous transformation. So cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, this matrix is going to be the rotation matrix. Rotation matrix captures just the rotation. But these two frames are translated by some amount. So somehow we need to capture that translation. So we populate this homogeneous transformation matrix. The last row is going to be 0, 0, 0, 1. And the fourth column, the first row would be the distance in x dimension between the old frame or new frame and the old frame. But the coordinate system will be the old coordinate system. Do you agree with me? Which means you will see how far that frame 1 is with respect to frame old, which is 0th frame, in the old coordinate system. So you need to translate A2 units in x0 direction, A1 unit in z0 direction. But this relationship is valid when theta is equal to 0. We want to make sure, since this frame is rotating, this relationship should be valid for all the values of theta. So you need, if you look at that figure from the top, if you have A2 something like this, A2's projection on x0 is going to be A2 cosine theta. A2's projection on y0 would be A2 sine theta. Everyone understood this? And the z distance will not be affected no matter whatever the value of theta is. Z distance will not be affected no matter whatever is the value of theta. Everyone understood this? Now, I want to ask you one question. I need to construct 0h2. I need to construct 0h2. To construct 0h2, first I need to construct 1h2. So to construct 1h2, I need to construct 1r2, which is the rotation matrix that is relating the first frame to the second frame. So we did 0th frame to the first frame. Now we are going to do first frame to the second frame. And that is where we will stop. Why? Because this robot only has 2 frames. So 0th frame, first frame, and second frame. Can you see this rotation is about z axis? This is about z, which means same rotation matrix will be used. Cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Are you with me? And this guy should also be multiplied with the projection matrix. Now, can you tell me it would be projection of what axis onto what axis? Projection of new onto old. Which is the new axis? New axis is x2, y2, z2. Which one is the old axis? x1, y1, z1. And now I want you to look at and tell me, and we did this exercise before, can you see x2 is aligned with x1? y2 is aligned with y1. z2 is aligned with z1. So do you agree with me that the projection matrix is going to be an identity? And why are we getting identity matrix? Because when we started, we assume x2 is in the same direction as x1. If I would have assumed x2 is the opposite direction of x1, then the negative sign would have popped in. And then to find the actual rotation matrix, you have to multiply these two matrices. So there is one more matrix multiplication. But here, everyone agrees that x2 is aligned with x1, y2 is aligned with y1, and z2 is aligned with z1. So this matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And since this is an identity matrix, multiplying rotation matrix by identity matrix gives me the same rotation matrix. Everyone agrees? Now I have to construct the homogeneous transformation. Constructing homogeneous transformation is no big deal. This homogeneous transformation would be 1h2. And this homogeneous transformation, the first 3 by 3 matrix is going to be the rotation matrix that we derived here. So 1r2. This is the rotation matrix that needs to go here. Please note, in homogeneous transformation, you have to use this matrix, not this matrix. In this case, this matrix is equal to this matrix because the projection matrix is identity. But I promise you that this projection matrix can have negative terms. One could be flipped, and in that case, you have to carry out the multiplication explicitly. So this matrix needs to go here, not this matrix. Everyone understood this? Very important. So I will write this rotation matrix, cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. And then you are going to have 1 here and bunch of zeros here. Now we have to find out the relative translation. That relative translation will be distance between frame 2 and frame 1 in the coordinate of frame 1. So basically x distance around x1, y distance around y1, and z distance around z1. Now let me ask you this. Can someone tell me what is the x distance between the frame 1 and frame 2 in the coordinate frame x1? Do you agree with me? It will be A4 cosine theta 2, just like the previous case. Everyone understood this? That distance between two coordinate frames, that equation has to be valid for all the values of theta. Why? Because please note that joint is going to rotate. We are solving the three-dimensional kinematics problem where the things move in 3 dimensions. So that's why this is going to be A4 cosine theta 2. What would be the y distance around y1? A4 sine theta 2. And what would be the z distance along z1? A3. Everyone agrees? Once you get correct rotation matrices, correct Fourier transformations, your forward and inverse kinematics problem is solved. What is a forward kinematics problem? Forward kinematics problem is nothing but going from 0th frame to the second frame. How do we go from 0th frame to the second frame? We start from 0, we go to 2, which is nothing but 0 to 1 and 1 to 2. Now same thing you can do it. If you want to find out the relative rotation of frame number 2 with respect to frame number 0, relative rotation of frame number 2 with respect to frame number 0, you would do 0 R1 multiplied by 1 R2. And do you agree with me that we have 0 H1, we have 1 H2, we have 0 R1 and 1 R2. So what we need to do is, we need to perform matrix multiplication. In today's class, I'm going to perform these matrix multiplications by hand. So first row, first column, first row, second column, first row, third column, first row, fourth column, second row, first column, second row, second column. I'm going to do that. But next class onwards, we will use MATLAB to solve these multiplications. But for the first class, I'm going to do these multiplications. You will follow, you will check my steps and make sure that I'm not making any mistakes. Okay, so I'm going to multiply. So I'm going to write 0 H1 multiplied by 1 H2. So this matrix, and you can correct me if this matrix is wrong, cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0. Here, can someone tell me what is it? A2 cosine theta 1, A2 sine theta 1, A1, then I have 1 over here. Now this 4 by 4 matrix needs to be multiplied with the second 4 by 4 matrix, and please check, this is cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1, 0, 0, 0, and this is going to be A4 cosine theta 2, A4 sine theta 2, A3 and 1. Do you agree with me? Now I have to perform this long multiplication. Just in case, I hope you know how the matrix multiplication is carried out. First row multiplied by first column. So cosine theta 1 will get multiplied with cosine theta 2, minus sine theta 1 will get multiplied with sine theta 2, 0 will get multiplied with 0, and A2 cosine theta 1 will get multiplied with this 0. Everyone comfortable with matrix multiplication? So the first term is going to be cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. Do you agree with me? First row, second column is going to be minus cosine theta 1, sine theta 2 minus sine theta 1, cosine theta 2. Do you agree with me? First row, third column is going to be 0. Please check my calculation. First row, fourth column is going to be A4 cosine theta 2, cosine theta 1. Then I would have minus A4. So first row A4 cosine theta 1, A4 sine theta 2, A4 sine theta 2, sine theta 1, and then I'm gonna have the last term. So it's gonna be A2 plus A2 cosine theta 1. You agree with me? Second row, first column, and that's gonna give me sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 minus sine theta 2 sine theta 1 plus cosine theta 1 cosine theta 2, 0, and what I would get here, so it will be A4 cosine theta 2 sine theta 1 plus A4 sine theta 2 cosine theta 1, and last but not least plus A2 sine theta 1. Do you agree with me? Third row, first column is going to be 0, 0, and here there will be 1. And the last one will be A1 plus A3 and 0, 0, 0, 1. You agree with me? Now check this out. This matrix that you have here is nothing but 0 R2, which is the relative rotation of frame 2 with respect to frame 1. I don't know. Do you see a pattern here? Remember sine and cosine formulae? What is this first term? Cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. Do you agree with me? This is cosine theta 1 plus theta 2. Right? Expansion formula. Do you agree with me? Now tell me, what is the second formula? If you take minus outside, it's sine theta 2 cosine theta 1 plus cosine theta 2 sine theta 1. So this is sine theta 1 plus theta 2. Do you agree with me? You have 0 here. What is this? Sine theta 1 cosine theta 2 cosine theta 1 sine theta 2, which is sine theta 1 plus theta 2. And what is this? Sine theta 1, sine theta 2, cosine theta 2, cosine theta 1, cosine theta 2, which is nothing but cosine theta 1 plus theta 2. This is 0. And then I have 1. This matrix is looking like the rotation about Z matrix, right? So something interesting is happening here. And let's figure out what is happening. Now, in this expression, I'm going to take A4 outside. If I take A4 outside, cosine theta 2, cosine theta 1, minus sine theta 2, sine theta 1. So you agree with me? This becomes A4 cosine theta 2 plus theta 1 plus A2 cosine theta 1. Next thing is A4 sine theta 1 plus theta 2 plus A2 sine theta 1. The last one is A1 plus A3, and we have 1. You agree with me? So what I got here? I got a very simplified expression, and I got a simplified expression. So this tells me that this is the distance between the frame 2 and frame 0 in x0. Frame 2 and frame 0 along y0. Frame 2 and frame 0 along z0. And if you look at this equation, this makes perfect sense. So now what I'm going to do is, I'm going to draw this diagram. So this axis, horizontal axis, is x0. Vertical axis is y0. Z0 is coming towards us. So the first robot, I'm going to show you the first link. And then I'm going to show you the second link. This link is A2. This link is A4. This angle is theta 1. This angle is theta 2. Do you agree with me? I draw a horizontal line. So this angle becomes theta 1. So if I find the projection here, this is going to be A2 cosine theta 1. And this guy is going to be A4 cosine theta 1 plus theta 2. Are you with me? This vertical distance is going to be A2 sine theta 1. And this distance is going to be A4 sine theta 1 plus theta 2. And in case if you are wondering, so I want you to kind of draw vertical lines. So A2 cosine theta 1, A2 sine theta 1. Since theta 2 is with respect to the direction of A2, so this angle is theta 2. So the angle made by this length with respect to horizontal is theta 1 plus theta 2. So you get this component. Do you agree with me that my x distances and my y distances are same as I got from the rotation matrices, homogeneous transformation? The z distance cannot be written down here because I'm showing you a planar figure. Do you agree with me? Now let's look at the rotation. Do you agree with me? This rotation matrix that you are seeing is telling me that frame 2 is rotated by theta 1 plus theta 2 with respect to frame 0. Can you see the top rotation matrix is telling me that overall rotation about z is theta 1 plus theta 2. Do you agree with me? This rotation matrix follows this rotation matrix that I have shown here, follows the same format of the rotation matrix that we derived. Only difference is instead of theta, 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 it's theta 1 plus theta 2, theta 1 plus theta 2, theta 1 plus theta 2, and theta 1 plus theta 2, which is telling me that the frame 2 is rotated by the total amount of theta 1 and theta 2 with respect to the frame 0. And that is true. Can you see the overall rotation of frame 2? This frame 2 is going to be here, right? The frame 2 is going to be here. Can you see that this frame 2 is rotated by theta 1 and it rotated by theta 2. So overall rotation of this frame 2, which is x2 and y2, this overall rotation is theta 1 plus theta 2. Everyone understood this? That is what is captured in this problem. Before I give you the quiz, any questions about the material that we discussed today? So today's class, we talked about the different types of robots. We talked about the robot configurations. We talked about the projection matrices. We talked about the rotation matrices. We looked at formal definition of forward kinematics, inverse kinematics, and then we derived the forward kinematics for a two-dimensional, 2 degree of freedom robot, which is shown the 3-dimension here, kinematic diagram here, and at the end you are gonna get, once you solve this, so whenever you solve forward kinematics problem, try to see that if you use geometry, you are able to do the same, you get the same solution. Everyone understood this? Now I'm gonna give you the quiz problem. Once again, for quiz problem, you should be using just the notes, handwritten notes for today's class. And you can use pen and paper. What I would do is, since I'm feeling very generous, I would leave my notes onto the board. So that way, in case if you want to refer to something, I will leave my notes onto the board. But I will give you the quiz problem. And the quiz problem, everyone ready? So TA is here, Mohammed. Mohammed, make sure all the laptops are closed and phones are stored. If you see any student using the laptop, tablet, phone, take a picture and give them 0. Only on the paper. only on the paper. And if you want, I'll give you 5 minutes to copy down your notes. So I'm gonna leave these notes here. I'm gonna